Okay, welcome to your video lecture for section 6.4, which will be solving differential equations with discontinuous forcing functions. Okay, so here we're just going to work through an example here. So let's look at the initial value problem. Y double prime plus 4y is equal to the Heaviside function centered at pi minus the Heaviside function centered at 3 pi with homogeneous initial conditions. If we take the Laplace transform of both sides, we will have s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 plus 4 times the Laplace transform of y is equal to the Laplace transform of the Heaviside function centered at pi, which is e to the minus pi s over s, and that of the Heaviside function centered at 3 pi, which is e to the minus 3 pi s over s. The homogeneous initial values cause those two terms to go away, and so if we multiply both sides by 1 over s squared plus 4, we end up with this equation for large y. Decomposing 1 over s times s squared plus 4 into partial fractions yields the following equation for y. Okay, so you can go ahead and do that on the side. You know that this would imply that 1 over s times s squared plus 4 would then have to equal 1 over 4s minus s over 4 times s squared plus 4. Okay, so plugging that in, we know that the inverse Laplace transform of 1 over s is just 1, and the inverse Laplace transform of s over s squared plus 4 is cosine of 2t. And so using that coupled with the theorem in the previous section regarding what happens when you multiply by e to the minus cs, we end up with this as our solution. The Heaviside function centered at pi times 1 minus cosine of 2t moved over pi units, and the Heaviside function centered at 3 pi times 1 minus cosine of 2t moved over 3 pi units to the right. Okay, taking a look at the solution here, notice due to the homogeneous initial conditions, the solution is 0 until you get to a pi, and then thereafter it has a little bit of character. It has basically a cosine wave shifted up about half a unit, okay, and then at about 3 pi right here, the right hand side is turned off again, and the solution becomes 0 again. And so that is due to the forcing term, which was u of pi minus u of 3 pi. In the interval 0 to pi and then 3 pi to infinity, the forcing term is 0. That coupled with the homogeneous initial conditions would elicit a 0 solution. But in the interval pi to 3 pi, you have the dynamics being forced, and thus a solution that's not 0 in that interval. Okay, thank you.